My name's Richard Hanson-Graville. I'm the Technical Director at Heatweb Solutions. Okay, my talk today is about heat network optimization. So our role for the last year really has been focused on improving the efficiency of heat networks, optimizing them. Just to give you got a few slides just to give you a feel back for our history, and why we're in this role. So we've been contributing to guidance since probably like 2002. So we were original authors of the Building Services Design Guide. We've contributed to CP1, Heat Networks Design Guide, the new MENA Water Treatment Guide. So there's really very little guidance written out there over the last 20 years that we haven't been technical authors for. And just shown here is an example of, this is one for Phil, so about a year, no, this is about 10 years ago, we did an event at the UK DEA where we pointed out a lot of issues with the current systems that helped motivate things such as the translation of DS439 to English. Just minor points that we need. Our background, why we contribute to standards. So this is going back. We have a long history. Going back to the 80s of continuous product design, from the very first prefabricated package systems. We invented the heat bank thermal stores, the first plate heat exchanger thermal stores, the first multi-fuel renewables thermal storage systems, heat banks. Commercial HRU sets, we were the first developers of those. We had HRU designs going back as far as 1998 and before. So the data HRU was one which a lot of people heard about. It had the best beta results for 5 years on the trot. But the idea is it's a continuous product development. So we live at the edge of actually designing products, and research and development is our core skill. This is probably one of the products is most relevant, so it's the data HRU. So this is the HRU that had the best results through beta testing for about 5 years on the trot. We got pretty well near theoretical perfection on our second test with a VART of 15.8, which isn't possible anymore because of the changes in the standard, but it gives you an idea of why we write standards. It's because we have a history of setting the standards. Okay, so I'm going to go back to this slide just to give you a sense of why we went for the theme. So we've come out of the manufacturers. So as an OEM, going back a long time, we have design skills, we have CAD skills, we have maintenance skills. So we had when the shareholders thermal integration shut the business down last year, we wanted to continue. So the engineering teams are still in place. We still have the skill sets, and we've added to the team as well. So the team now consists of. All the members of the team are very skilled in their own areas. So these may be, system design, BMS, gas boilers, legal side of things. So everyone on the team brings something to the team. And when we try to take on new recruits, we take on students, but we also try to bring in engineers and bring a new speciality into the mix. So we look for engineers who really do top of their game, and that's they can contribute then to our skill set and our best practices. Okay, so the roles of an optimization engineer. So we thought it might be worth to bring it back to basics of what actually is our role in life, because this helps define our company purpose. The little figure in the bottom right, it helps to define what we do, which is Archibald Harry Tuttle, which is, if anyone's seen the film Brazil, he's the sort of plumber that goes out there and tries to fix heat networks. You must watch it. If you haven't seen it, I strongly suggest you watch the film Brazil. It's yes, the parallels are quite amazing. So the role is to improve reliability of building services. I mean, that's the main thing. We're going into buildings to fix them. So improving reliability is the first thing. So stop them failing, people have their services. It's to improve the energy efficiency and reduce carbon footprints. So reliability is first, and efficiency comes second. Then it's to move fossil fuels towards a net zero. So we've got them working, we get them efficient. Now there's a journey to be had to get everything to net zero. It's part of our role to identify the processes that improve outcomes for end users. So specifically, it's about identifying the processes that that results in end users having better systems, more efficient systems. It's to disseminate knowledge, processes, guidance, and training. So optimization engineers are working out the best ways of doing things. So they are developing the knowledge that needs to be transferred to everybody. Because, I mean, this is a worldwide mission to get to net zero in the next 10 years. It's not something you can do in isolation. So the role of optimization engineers is to work out how things work together and to make sure everyone's clear on these. And probably one of the most important ones is to reduce the costs and burden of QA processes. So it's very easy as a QA engineer to rub your hands together and think lots of money to be made out of optimizing, but that kind of misses the point. We're trying to improve the method itself of optimizing. So we're optimizing in a sense, to just try and get quality assurance processes in place that are effective, but don't take up loads of time. So we're looking for effectively the most effective ways of ensuring a proper outcome, not layering on as much as we can. Okay, so technical areas. So one of the things is when we're looking at stuff is I mean, we used to be HIU manufacturers. Now we're in a sort of a role doing everything. So we've sat back a bit, and when we're doing stuff, there's a lot more stuff that needs to be targeted than just HIUs, obviously. So just to run through a list of the kind of things we're tackling: metering infrastructure and accuracy. As Steve was saying, like gas boilers, it's meters are missing everywhere, and they are where you start with optimizing. Without meters in place, you know, you're on a losing mission. Central heating systems, HIUs, distribution pipework, bypasses, substations, water quality, DP sensing and pump control, buffer store arrangements, boiler loading, boiler sequencing, set points of gas boilers. Like Steve was saying, that the efficiency of a gas boiler can be remarkably far off where you thought it was just by a few set point changes. Specialist knowledge relating to heat emitters needs to be in place soon. The quality control, it can't wait for the next time. Temperature dilution. If you've got lovely returns on your network, you still may have horribly inefficient boilers because everything's getting mixed up. CHP integration, air handling systems, fan cool units, and MVHR systems. So we've been doing a lot on these things because really very few other people have been. Heat pumps, COP. So like I said, we've been optimizing the world's first CO2 heat pump systems. Cooling systems, BMS point-to-point, BMS control, alarms, frost functions, and benchmarking efficiency. There's a lot there, but the idea of this is really to give you a feel that everything needs to be tackled at once in unison, and we need to sort of at least have the picture in front of us of what we're trying to tackle. Data sources. So in our job of fixing things, you need information. Just to give you a sense, if we use things like historic consumption data, historic meter data, schematic drawings, plant room drawings, site surveys, 3D scan surveys, discussions with end users and operators, some clamp-on monitoring, live BMS data, live AMR data, and weather data. So these are our sources that we go into our report writing calculations with. Okay. One of the first things we do in benchmarking is we try to describe the efficiency of a network, pin it down to two numbers. It's a bit like VARTs for HIUs. So for networks, we have a fixed basic summer load and then a variable load that is to do with outside temperature, your heating load. This graph here shows, this is actually a live site of 1,000 properties. The green is historic gas consumption. The red and blue lines are two effectively before and after optimization curves. So you can see how the green tracks the red line before. That gives us our P&U values before optimization, and after the optimization we're on the blue curve. So it's a methodology for pinning down the efficiency of a heat network so you can predict the load given any weather conditions. And if things don't match these curves, the alarms go off. So every site should match a curve, and if it doesn't, there's a reason. And it allows you to keep track for any given weather conditions, whether the actual efficiency of the site is upping or downing. So that's quite a key one, is benchmarking. Okay, I'm going to jump to NVHR optimisation. Now, this might seem a bit strange given that we're talking heat networks and cooling networks, and these don't actually connect to them. But they are an integral part of the property's energy system, as is the heating and cooling systems. Without the proper commissioning, acceptance testing, maintenance, properties will deteriorate. So for 10 years or so, we've been going in everywhere without air bricks. We've been warned by NVHR manufacturers that there's a very big problem coming our way in the sense that none of these have been maintained for 10 years. And now you have a generation of house building that's going to be effectively becoming damp at the core because it hasn't had correct ventilation systems in place. The drawing on the right there is an NVHR unit in a district heating along with a heating unit and a cooling unit. And behind a little panel in the bottom right is a sort of attempt at a BMS system to get them all working together. So these things are thrown into new build to work as a system to tick your boxes, but they're never commissioned to work together. So the point of this slide is we have to tackle these things as a whole energy system, not just take off little chunks. They have to work be compatible with each other. Just little things like NVHR units pumping all the heat out of the building that you're generating. That's commonplace, this sort of stuff, because very few people actually look at the system as a whole. But we have to. From now on, we have to look at systems as a whole. And that starts with commissioning. So, for example, NVHR, HIU, central heating and cooling commissioning all needs to take place. Really, commissioning sheets should be worked out as a whole. And hopefully, we're doing it with new build recently. They're done as a single team. So the acceptance test in the commissioning process is done very efficiently, very effectively. We know everything in the properties is perfectly working with each other. And this sort of approach should be rolled out. So we're a lot about trying to nail down commissioning practices and the processes and putting them out there as open source so that people can copy. To help in this, so we've been within MENA, so we've been in the Manufacturer Heat Networks Equipment Association for a number of years, and we're still in there. One of the things that we're working on is something like benchmarking apps. So we've, in our usual style, we've gone and written one, open sourced it. So this is available to anyone to use now. So this is a full commissioning app that does HIUs, direct, twin plate, and it can be customized as well. We're putting in there NVHR central heating commissioning. So this is, again, it's like I say, it's an open source system that manufacturers can collaborate on to make sure that the benchmarking questions align with their products. But it's out there. You can go and start using this tomorrow. And it's probably one of the most thorough benchmarking apps that you'll ever see. Okay, moving up from NVHR to the bigger stuff. There's a lot of this stuff out there that we've been optimizing. So on the right there, that's an air handling unit with heating and cooling on it. That one particular one is doing the Birmingham International Conference Centre. On the left is a graph exported from the air handling systems in the Excel Centre. So the exhibition halls, we've been working with them for the last year to optimise the heating. So in the exhibition centre, above your ceiling, we have some of our kit. This slide sums up the problems that we found. So we have heating and cooling running together in parallel. We have the heating going on at full guns right up to the moment the cooling kicks in, and they're overlapping. And we're not talking small amounts of energy here, we're talking colossal amounts of energy. Hundreds and hundreds of houses worth of energy here. It takes a bit of visibility on a system like this first to then address it. So once you see the problem, for the Excel Centre, their own internal BMS engineers took it from here. So once they're aware of the problem, they can then start addressing them and fixing them. So their energy efficiency improved significantly because they've been able to change the PID to simple BMS control routines. Once they know it's there, they can look out for it. Pump energy and DP optimization. So this is a function on every heat network. It's common, it doesn't run. There's some keys to getting it right. First is the correct choice of sensor. Second is the correct choice of communications to get the data back to a plant room. And the third is having the correct BMS control schedules to actually pump control. So this is sites we're working on. We're looking at the visibility of the pump controls. This is quite typical when you look at pump controls. You see that they do weird stuff. And if you look at pressure sense data, you understand why. So adding visibility to DP sensors and pump speeds is really easy, and it's very low hanging fruit. These pumps can be running at 11 kilowatts. I mean, that's £20,000 of energy a year per pump. If you knock that speed down by changing DP settings, you can have some instant savings. The pay for optimization works from day one. You can get ahead of the game. Your savings are straight away outstripping the costs. Substation optimization. So we do loads of substations. They're everywhere on the city schemes. You've got your normal things like VARTs, temperatures. We've been working on a metric to describe a plate heat exchanger, so a plate heat exchanger efficiency figure, which I'll go into a bit later, but it's a nice figure. It basically tells you if a plate's working. It tells you how close the approach temperatures are. So here we have a secondary return on the other side of 58, but was going back to the network at 69. That's really poor efficiency, which is reflected in the metric. But we've been a lot about trying to how you spot the problems through the data, how you can overlap some simple metrics on top of your BMS and all the problems jump out and direct your works. Right, this is a big one, point-to-point testing. So BMS systems have thousands of sensors, and the reason why generally a lot of systems don't work is because the wrong sensor is connected to the wrong input, or they don't work. So this is an example. 2 plate heat exchangers on a substation with a heat meter. If you look at the plate heat exchanger sensors versus the heat meter sensor, they don't match. So they're different colours. That's an alarm. That's been going for years, no one knowing that. And across this site, we had meter sensors loose, and no one knew until you looked at them against the BMS sensors, and straight away it's like, well, that's not right. They should look like they are on the right, all matching, all the same colour. So this is a very, very quick, easy way by correlating your BMS data points with your meter data points to suddenly see a lot of problems on site at acceptance testing. So we went straight for 30 sensors that we knew wrong the day after loading this up. No one even knew for 5 years that these sensors were faulty. There was no way of knowing them unless you started cross-referencing. So we're developing little tools that really simplify the whole process of quality control without the need for testing of labour. The whole point about this is it's BMS driven, which we'll get to later. Another system, buffer stores. So we've manufactured thermal stores for a very long time. This is a typical, maybe not typical, but a buffer store arrangement, three buffer stores in parallel. Boilers were connecting from the left, the load is on the right. So the store on the left is getting hot all the time, charged from the boilers. The store on the right is cold because that's got the network, and the return's getting diluted. So if you ever see buffer stores installed like this, it's not going to work. It might look like it's working, but it won't be working efficiently by any means. It will not be loading and discharging, as you can see in the graph on the bottom right. So the process of optimizing here was to take this arrangement and change it to a reverse return. Now that's no small task. So again, the core principle in our company is we want to be able to go from end to end without any snags. We want to optimize the problem and not have to we have to hand over to someone else for this stage. So that took 3D scanning because there's a lot of complicated pipe work at high level. The drawings were not really fit for purpose. So that's the results of the 3D scanning of the plant room. It took us a few days to do the scanning and come back with this model of all the pipe work, and this gives you an idea. Different coloured pipe work was showing the different options we were for upgrades. So this site we then upgraded in partnership with Thames Flame. We did it in a single overnight shutdown, starting at 11:30. We changed about 40 metres of 6-inch pipework, installed new loading valves, transformed the operation of the buffer source system, and the network came back to life by 6:30 in the morning. So nobody in site knew this had happened. This is major buffer operation. So that that's the sort of where I refer to these guys, especially Thames as a sort of special forces. We can go in and fix these sort of problems, which will just go on for years. You need a proper approach, you need a proper strategy, and you need a plan. And when you've got that in place, it can go start to finish quite smoothly. And again, it's all data driven, so that we're watching it as we go. And an integral part of those kind of works is the BMS. So this is that system, the BMS head end. 3 buffer stores, CHP system. We've done a huge amount of work on the actual BMS. So as manufacturers, controls logic is our forte. That's how we got the best pizza results in the industry, through our controls logic. So now we've got into BMS systems, we're able to update their controls logic with the same mentality that we took approach to designing HRUs, which is standardizing and feedback. So the works there, we did the works overnight. The BMS was adjusted the same night, so come the following morning, the entire site was running, mechanically and electrically programmed, quality controlled, and visually and visible to the client remotely. So, okay, I'll hand over now back to Jason, who will show you some of the even bigger stuff that we've been working on. Okay, thank you.
Up next is Steve Harper. Steve's come to join us from Elan MEP, and they are an independent MEP consultant and heat network assessor. So this is going to give you a broader idea of the industry, which isn't so much of a sales pitch from the Heatweb guys. So if I can invite you up, please, Steve.
Thank you.
Okay.